Hello, in this recording, I wish to pick up some questions from the homework for the week of 13 on L'Hopital rule. We did some examples in class, but I just hope you guys will do some homework. And I just pick up questions I thought might have problem with. So here we go. We're going to get started. I'm going to select a couple questions. For example, the first question of my choice would be with a trig function. Okay, example number 1. The first one is that we're taking limits. And this limit, this limit is limit as x approaching 0, and we're taking limit of tangent 3x over sine 2x. Okay. When we apply L'Hopital rule, every time we apply, we must check the condition. Okay, these two conditions are, number 1 is either both the numerator and denominator approaching 0, then we can use the L'Hopital rule and take the derivative of the numerator and denominator separately, respectively. Okay, not quotient rule. If this condition is satisfied, then we can apply L'Hopital rule. Okay, the second case, okay, would be that if we check the condition that the numerator and denominator approaches the infinity, it doesn't matter negative infinity or positive infinity, in that case, we can also apply L'Hopital rule. So it's either 0 over 0 case or infinity over infinity case, and doesn't matter positive infinity or negative infinity. Okay, so these are the key components of L'Hopital rule when we use them. Okay, so now without further ado, so here in this part of the homework, okay, don't only think of using L'Hopital rule. Sometimes other method may apply, and other method may be even, maybe even better to find the limit. Okay, so here we're going to check the condition, right? When you check the condition in terms of how to show your work, preferably you check your condition on the side. Okay, on the side. Do not mix it with your work. Okay, for example, I would put it in my on my scratch paper. This is my scratch paper, right? So don't put them on the same, together. So think out loud. I check. Okay, when limit is x approaching 0, and tangent 3x is a continuous function, it approaches 0, right? And when we take limit sine 2x, when x approaching 0, that limit is also 0. So I'm taking the condition. You don't necessarily put those conditions in between the lines, and put them separately will be so much nicer. So this limit, so in that case, we can apply the limit law, right? So we take a derivative of tangent 3x. The derivative of tangent 3x, we take a derivative separately, okay? We take a derivative of tangent 3x, which is going to be, of course, we're going to apply chain rule, right? The derivative of tangent u is secant squared 3x. And then we have to take a derivative of 3x. So we're going to have a 3. So it'd be better we put the 3 in the front. Right, so the numerator, we found the limit is 3 times secant squared 3x, and we take a derivative of the denominator. The denominator, the derivative is sine 2x, right? So we take a derivative separately. And that derivative, and we apply chain rule again, so cosine 2x times 2, so we're going to put the 2 in the front. All right, the denominator is 2 times cosine 2x, okay? And then when we decide what are we going to do next, right? When x is approaching 0, the denominator actually approaches 1 because the cosine 0 approaches 1, and secant square is also approaching 1. So in this case, the L'Hopital rule conditions are not satisfied. We cannot use L'Hopital rule. And then what do we do? Right? So in this case, we have to think of using other means. But what are the other means can we use? Well, we just mentioned as x approaching 0, the denominator is approaching 1, cosine 2x approaching 1. Well, this is great because this whole thing is a continuous function, is continuous at 0. So we can just do a simple direct substitution. Okay, so here we're going to multiply x, replace x by 0, direct substitution. So the limit symbol can be removed. So in the end, we are getting 3/2. We're getting 3/2. Okay. Do you need to show these work? You don't have to. All you have to do is checking the condition and continue the steps. And whoever reads your work should have some basic knowledge, right, about the condition of L'Hopital, applying L'Hopital rule. So that's it. Okay, so let's look at the second example. Example number 2. Okay. This one we have limit and x approaching 0 again, and we have x squared over 1 minus cosine x. All right. Well, when x is approaching 0, obviously the denominator, well, cosine x is approaching 1. So denominator approaching 0, numerator approaching 0. So L'Hopital rule applies. If L'Hopital rule applies, right? So you can just go directly to take a derivative of the numerator and the denominator respectively. So we have 2x on the top. In the denominator, we have derivative of 1 is 0. The derivative of negative cosine x is going to be sine x. Okay. Now, what can we do? Can we do direct substitution? No, we can't, because we have sine x when x is approaching 0, denominator approaching 0, numerator approaching 0. So we cannot do direct substitution. But in fact, we can use L'Hopital rule again. The derivative of 2x is 2. The derivative of sine x is cosine x. So the next step, yes, we can do direct substitution, and that's going to be 2 over cosine 0 equals to 2 in the end. Okay, so these examples are fairly easy. Okay, let's look at another one that involves logarithm. Okay, example number 3. Okay, we have a limit situation. Okay, limit as x approaching infinity. Okay, and a quotient with ln the square root of x. Okay, and the denominator is x squared. What can we do? Well, depends on whether you want to do something about ln x. right? You can do something about ln x. As x is approaching infinity, we have this setting, right? The numerator is approaching infinity, the denominator approaching infinity. So the second condition applies. But we can also use power rule, okay, to make this 1/2 of ln x. Okay, so this is still, we can still apply L'Hopital rule. We take a derivative of the numerator. Whoops. We take a derivative of the numerator. And we take a derivative of the denominator. So over here, wait. Okay. The derivative of ln x, of course, is, well, keep the 1/2. We could actually put it in the front of it. Is equals to 1/x. The denominator, or the derivative, is 2 times x. Okay, and we can do some reduction. Okay, we can do some reduction. And what we get is 1/2, and so here is a 4. Okay, and 1/x, and we can get it to, we multiply x on the top. Okay, principle number 1, anything times 1 stay the same. So we multiply x on both top and bottom. X is approaching positive infinity, so x can be any positive number you can think of, right? So we can do this. And now the limit has become in this form. And the top is 1, the bottom is x squared. When x is approaching infinity, well, this is going to be 0, limit is 0, right? The denominator approaching infinity. So that's example number 3. So let's look at another exponential form, okay? So this is example number 4. We observe a limit, okay? When t is approaching 0, limit, and we have a quotient. We have 8 to the power t minus 5 to the power t divided by t. Okay, let me make the font just a little bit larger. When t is approaching 0, denominator is approaching 0. The numerator, when t is approaching 0, is 1 minus 1. So it's 0 as well. So L'Hopital rule applies. So we're going to take a derivative of the numerator and the denominator. Derivative of the denominator is 1. The derivative of 8 to the power t is 8 to the power t multiply ln 8, subtracting 5 to the power t multiply ln 5. So we ended up with something like this. Okay, we can remove the 1, right? Divided by 1, it's just, we can just omit that. So we're taking limit of this. Now, when t is approaching 0, now we don't have a denominator, right? So L'Hopital rule certainly doesn't apply. But if you look at these functions, these are continuous functions. So it's a direct substitution. So when we do direct substitution, we simply substitute t by 0. Okay, because they're a continuous function. The limit of continuous function is just simply direct substitution. And 8 to the power 0 is equals to 1. 5 to the power 0 equals 1. So at the end, we have ln 5 and ln 8 minus ln 5. That's it. Okay. Now, Let's pick another question. Okay, this question once again has something to do with exponential, has a trig function, right? This will be example number 5. Example number 5. And the limit in our consideration is limit as x approaching 0. And we have x subtracting sine x over x subtracting tangent x. When x is approaching 0, the numerator approaching 0, denominator approaching 0, right? And L'Hopital rule does apply. Okay, but when we take the derivative of these functions, we will get the following. The derivative of x is 1. The derivative of sine x is a cosine x. The derivative of x is 1. The derivative of tangent x is a secant square. Okay. Then when x is approaching 0, the numerator is approaching 0, the denominator approaching 0 because the cosine x is approaching 1, and secant square when x is approaching 0 also approaching 1. So we can use the L'Hopital rule one more time. When we use the L'Hopital rule one more time, on the second time, of course, we check the condition, and we take derivative of the top, that's going to give us sine x. Right, the derivative of 1 is 0, the derivative of negative cosine x is sine x. Then the derivative of negative secant square, this is we're gonna use the chain rule. So we're gonna have a -2 secant x, and then the derivative of secant square, that's going to be secant x multiply tangent x. Okay. I hope I'm right. I think I'm right. Okay. So now what do we get? Now what do we get? We're going to simplify this function. Okay. We cannot apply L'Hopital rule and again, unless we check the conditions are satisfied. But in this case, we must simplify. So secant x times secant x, that's a secant square. Okay, when x approaching 0, secant square x approaches 1. Tangent x when x approaching 0, that is approaching 0. That approaches 0. However, let's try to simplify this, right? Tangent x is equals to sine x over cosine x, right? And the sine x will reduce with the sine x on the top. So on the next step, we can reduce these two functions, right? And the secant squared, and this is another secant function. This is another secant x. So we ended up with the secant to the power 3x. And when x is approaching 0, denominator approaching not a 0, so we cannot use L'Hopital rule. The numerator is 1. So it's a direct substitution because this function is continuous at 0. So we simply replace x by 0. So in the end, we get a -1/2. Okay, you can see it involves some trigonometry simplification. The next one, okay, the next one. Let's see, I don't want to make this too long. Okay, let's pick one that has trig functions and exponential functions. Okay, so this is the example number 6. So we have a limit as x approaching 0, right? And we have a quotient form e to the power x minus e to the power of negative x minus 2x and x minus the sine x. Let's see if I copy the question correctly. I think I did. E to the power x subtracting e to the power negative x minus 2x. When x is approaching 0, e to the power x approaching 1. So this is approaching 1. So 1 minus 1 is 0. X approaching 0. So the numerator approaching 0. Denominator is a 0 minus 0. So we have a form that is 0 over 0 form. So we can apply L'Hopital rule. Okay, so we're going to apply L'Hopital rule. Okay. The numerator, the derivative of the numerator. So we're going to take a derivative of each one of these one by one. The derivative of e to the power x is e to the power x. The derivative of e to the power negative x, we're going to have to use chain rule. Okay, and then we take the derivative of negative 1. Subtracting 2, the derivative of the denominator is 1 minus cosine x. And then let's organize the term a little bit. Let's organize the terms, right? So what do we have here, right? Denominators stay the same. Numerator, we have a negative, and there's a minus 1. So we have e to the power x plus e to the power negative x. Oops. E to the power of a negative x minus 2. So now what do we get? If x is approaching 0, the numerator is going to be approaching 1 plus 1 minus 2, approaching 0. Denominator is approaching 0 again. So we can use the L'Hopital rule one more time. The derivative of e to the power x is e to the power x. The derivative of e to the power negative x is minus e to the power negative x. The derivative of 2 is 0. And this piece, we're going to have minus sine x. Now, what do we do? We have, when x is approaching 0, denominator approaching 0. Wait, I think this is a positive, right? The derivative of negative cosine x is a negative of a negative sine x. All right? Okay. So now we have 0 over 0 again. So we get to use the L'Hopital rule one more time. Okay. And the derivative of e to the power x, of course, is e to the power x. The derivative of negative e to the power negative x is going to be, the same story again. So it's going to be e to the power of negative x. The derivative of sine x is cosine x. Now, if x is approaching 0, denominator will no longer be 0. In fact, the whole thing is a continuous function. Right? Why is a continuous function? Continuous function, continuous function, continuous function at 0, right? They're all continuous functions. They're in the domain, and the denominator is not 0. The sum and quotient of these functions is also continuous functions, right? We learned that property before. So it's going to be just a direct substitution. E to the power 0 plus e to the power of minus 0, and that's cosine 0. And so finally, it's going to be 2 over 1. So the answer is 2. So you can see multiple examples of this sort, right? Next, let's look at some I think we can look at this number 44. So this will make it example number 7. Example number 7. Okay. Number 7, we have this limit. Limit as x approaching infinity. And we have a square root of x. Oops, sorry. We have a square root of x multiply e raised to the power of negative x over 2. It's not in quotient form. It's not in quotient form. And can we write it in quotient form? Because L'Hopital rule only can be applied if we write it in a quotient form, right? Certainly we can. This is negative exponent, so we can bring that part up under the denominator, right? So remove the negative sign. Okay, e to the power of x over 2. It was e to the power negative x over 2, right? So this is according to the property, just in case, b to the power of negative n is equal to 1 over b to the power of n, okay? The power rule. Definition. When x is approaching infinity, numerator approaching infinity, denominator is approaching infinity, so we can apply L'Hopital rule. The derivative of square root of x is 1 over 2 times the square root of x. The derivative of e to the power x to the power 2, and it's going to be e to the power x to the power 2 multiply the derivative of x over 2, which is 1 over 2. Right, so there's a half on the top, 1 over 2. There's a half in the bottom. So the next step we have the limit, right? And the half and half is gone. So we have square root of 1 over square root of x multiply e to the power of half x. When x is approaching infinity, that approaches infinity, that approaches infinity, so that 1 over infinity, that's going to be 0. And here, certainly we cannot apply L'Hopital rule, but we don't need to. We don't need to. Okay. All right. So let's look at a situation. Okay, let's look at a situation which is a little bit more complicated. Okay, but we're going to work on this together. Okay. Example number 8. We are looking for a limit. Okay, but this time the limit, okay, x is approaching negative infinity. And the function we have is x multiply ln parentheses 1 minus 1 over x. No obvious quotient form, so we have to do something to make that quotient form. And in particular, as x approaching negative infinity, this piece approaching negative infinity, and let's see what we get here. If x is approaching negative infinity, 1 over x is going to approach 0. 1 minus 0 is approaching 1. Ln 1 is approaching 0, right? So what kind of form is this? This is the form which is infinity multiply 0. This is the indeterminate form. In this is the indeterminate form, right? In order to find limit, one of the algebraic things we can do is that we try to see if we can make it a, so we certainly cannot simplify this algebraically, right? You cannot factor, you cannot reduce in any way. And you can certainly think of, make that one quotient and apply quotient rule, okay? But we'll try that just a little bit later. We just try that just a little bit later. So what we're going to try is that I'm going to do this. Okay. And I'm going to flip this x into 1 over x. So when x is approaching negative infinity, the bottom is approaching 0, the top is approaching 0. We have a 0 over 0 case, right? So we can apply L'Hopital rule. When we apply L'Hopital rule in the when we differentiate the denominator, of course, that equals to negative 1 over x squared. The numerator, what do we get? Well, we're going to apply the let's see, we can do something like this. Okay, we're going to take a derivative, right? Derivative of find common denominator. So that's going to be x minus 1 over x, right? And this whole thing, we're taking derivative. Okay, let me put something on think out aloud. Think out aloud. So what I'm doing here, I'm taking the derivative. Okay, I'm taking the derivative. Hold on. I'm going to smooth this. I'm trying to go a little slower. Okay, there. So I already took the derivative of the denominator right here. I'm going to take a derivative of this piece, right? To take a derivative of that piece, first I was going to do something inside here before I take the derivative, which is I'm going to make it a common denominator, right? 1 is x over x. Subtracting 1 over x. So this piece will give us ln denominator x, numerator x minus 1. Okay, let's see if we can do that. We do have a problem. We do have a problem. Okay, what is that problem? That problem is that because x is approaching negative infinity, right? I cannot write it this way. You say, oh, if I can apply quotient rule minus ln x, because x is approaching negative infinity, it's not in the domain. It's not in the domain, right? So we cannot do this. We cannot do this. So what could I do? So I'm going to just take derivative as such, as a chain rule. Okay, as a chain rule. So what I'm going to do is I'm going to do the following, right? I'm taking derivative of ln of such, so that's going to be equals to 1 over 1 minus 1 minus x, right? That's the chain rule. And then take a derivative 1 minus 1 over x. That's going to give us the derivative of 1 is 0, the derivative of negative 1 over x is positive 1 over x squared. So we apply chain rule. You see here, we can't use quotient rule. Okay. So now what kind of situation we have here? Well, okay, so just the note. Use log quotient rule. Okay, because x is approaching negative infinity. Negative number is not in the domain of the logarithm. Okay, so I hope that's clear to you. So then we simplify. When we simplify, certainly 1 over x squared takes away the 1 over x squared, right? So this will be negative 1, and this is the 1. So this is just as such. So we have basically, right, one more step. We just have a negative sign in front of it and remove this piece and put that piece right here. Now, when x is approaching negative infinity, this piece is approaching 0, right? We have a negative 1 over 1. So in the end, the answer is negative 1. There are a couple of details that I wish to go back to explain to you that, you could have tempted to say, oh, now I have reviewed the logarithm. I know how to use the quotient rule. We have to understand when we apply product rule, quotient rule, and it has to be done in the domain of the function. So we can't do that here. Okay. All right. Another one that might look a little bit challenging, and I'm going to, this is the example number 8, the example number 9. This one I have here is a limit, has some interesting power, Okay, so the limit goes like this, 48. Okay, limit as x approaching positive infinity. And over here, we have x raised to the power of 3/2 and sine of 1 over x. So what kind of situation we have here? Well, this piece approaching positive infinity, that piece approaching 0, because when x approaching infinity, 1 over x approaching 0. So we have an indeterminate form of infinity multiply 0. What's the limit? We don't know. What's the limit? We don't know. Okay, does it have a limit? We'll see. Okay. The tricks seem to be common. We're going to flip this part over. Okay. Create a situation maybe we can do something about. So once it's flipped over to the denominator, so this is going to become negative x raised to the power of or you can write it as let's write it negative. Okay, well, x is approaching infinity, and this thing is going to approach to 0, approaching 0. So we can apply L'Hopital rule. When we apply L'Hopital rule, and we're going to differentiate the numerator and denominator respectively, the derivative sine 1 over x cosine 1 over x. And then we have to differentiate 1 over x, which will give us negative 1 over x squared. The reason I write it this way is because we don't want to confuse. Okay, and the derivative of the latter one is equal to x. Okay, well, negative 2/3, or negative 3/2, sorry, negative 3/2 to the power of negative 3/2 minus 1. And then what we get, we're going to simplify, right? We're going to simplify. This is a negative 5/2, right? And this is negative sign, and negative sign, that's going to reduce, remove the negative sign. And what else? X raised to the power of a negative 5/2. Negative 5/2. Can we reduce these two? Certainly. You can bring the x squared down under x squared, right? And so these two powers can add up. These two powers could add up. What do we get? When we add up these two powers, right? That's going to be, this is going to be negative 2.5. So this is going to be negative 1/2. Negative 1/2. And then what? 3/2, if you flip over, that's going to be 2/3. right? And then what? As x is approaching infinity, as x approaching infinity, 1 over x is going to be approaching 0, and cosine approaching 0 close to 1, we cannot apply L'Hopital rule in this form. Then what do? We're going to put this over on the top, okay? Just flip it over. So now we get the following form, right? So x raised to the power negative half. I'm going to bring this just x raised to the power half, right? It become positive half. So we're back in this form. This is still different from what we were given. So there's a 3 over here. So you can write it as 3/2 if you like. Okay, 2 over 3, and that piece is going to be written like that. While x is approaching infinity, what is this approach to? Can we apply L'Hopital rule? We cannot. We cannot apply L'Hopital rule. So what will be the limit? Right? At this point, actually, I want to go back to check my work. Sine 1 over x, cosine 1 over x, negative 1 over x squared, because I feel a little stuck. Over here, okay, so negative 3/2 x raised to the power negative 5/2. I bring the x squared under, right? So I get x to the power negative half. And then I don't think I made any mistake at this point. But what is the limit as x approaching infinity? We have a square root of x. And this one we cannot make it into a form that is, that will give us a clear indicator of what will be the limit. At this point, what do we do? This is bounded, right? Cosine x is bounded. It's less than equals to 1, greater than equals to negative 1. And x is approaching infinity, right? X is approaching infinity. So this is the form of infinity times 1. And infinity times 1, of course, is going to be infinity. Okay, so this one doesn't have a limit. Or the limit is infinity. Does that make sense? If you have any questions, don't hesitate to ask me, because in the earlier case, it's infinity times 0, but now this one is approaching 1, right? And this piece is approaching positive infinity. So the total limit, or the final limit, is approaching infinity. Okay. One more trig related functions. Maybe one more, 2 more. Okay. Example number 10. We have a limit. Okay. This limit is very interesting. This limit is when x is approaching pi over 2. Okay, from smaller than pi over 2. And we're taking limit of an expression, which is a cosine x multiply secant 5x. Okay. I want to go over this example because I want you guys to be better at the trig functions. First of all, we know that Think out loud. Okay, when x is approaching pi over 2, when x is approaching pi over 2, what happened to cosine x? That's a continuous function. It approaches 0. Okay, secant. How about secant? Right? How about secant? When x is approaching pi over 2 from smaller than secant, right? X is approaching pi over 2, that's going to be secant 5 pi over 2, right? Secant 5 pi over 2 also it's approaching 0. So we have a 0 multiply 0 situation. No, wait. Oh, because secant 5x equals 2. Let me show you another thing. Okay. Secant equals to cosine 5x. Right? Secant 5x equals to cosine 5x. So when x is approaching pi over 2 from smaller, secant x actually is approaching infinity. So we have a form of indeterminate form, 0 multiply infinity. Okay, my bad. Secant 5x actually approaches infinity. So we have a 0 multiply infinity indeterminate form. So what can we do? What can we do? What we can do is that one of the things we can do, maybe the easiest thing we can do, is we write the secant part in the cosine form. Okay, this is what I meant. We're going to write it as 1 over, right? 1 over cosine 5x. Oops, sorry, this should be written this way. i.e., it is the cosine x over that. Okay. So once we write in this form, the numerator approaching 0, denominator is also approaching 0, we can apply L'Hopital rule. When we apply L'Hopital rule, we're going to take a derivative. The derivative of cosine x is negative sine x. The derivative of cosine 5x is negative sine 5x multiply 5. Right? And we reduce it. When we reduce it, this is negative takes away the negative, reduced, right? And then x is approaching pi over 2 from smaller than pi over 2. And don't forget, sine as x approaching pi over 2 is a continuous function and denominator is not 0. We can do a direct substitution. Good news, isn't it? Okay, so now we can do direct substitution using the continuity concept. So we're going to substitute pi over 2 into x. Removed the limit sign. You no longer need the limit sign. So now what do we got? This is 1. And this is 1. 5 pi over 2, right? And there's a 5. So in the end, the answer is 1/5. 1/5. Okay, so it takes some manipulation of these trig functions. Okay, now let's look at example number 11. This one is marked as a purple color. Okay, so there might be some challenges ahead of us. Okay, so let me just cut this and move it under number 11. So the think out loud still goes there. Oh, wait, this is actually a infinity, my bad. Okay, this is infinity. Okay. But I did say it's approaching infinity, okay? 11. 11, we have a limit situation. We have a limit situation that as x is approaching 0, and we have a cosecant x subtracting cotangent x. And apparently this is not a L'Hopital rule form. Okay, what kind of form is it? As x approaching 0, think out aloud, okay, to analyze what kind of form we have here. Cosecant x is equal to 1 over sine x. Right, so when x is approaching 0, sine x is approaching 0, so secant x is approaching cosecant x is approaching infinity. Okay, so when x is approaching 0, whoops, sorry. When x is approaching 0, okay, I mean to write it this way. When x is approaching 0, this piece is going to be approaching infinity. How about cotangent x? Cotangent x as x approaching 0, cotangent x, which is equal to cosine x over sine x, okay? As x approaching 0, denominator approaching 0, cosine x approaching 1, this is approaching infinity. So the indeterminate form we have here is infinity subtracting infinity. Infinity subtracting infinity, what will be the limit? We don't know, right? We don't know. So what do we do about it? We cannot take limits separately because limit law does not apply here, okay? Because each individual limit doesn't exist. All right, so what we can do, we can try a couple of things. So one of the things that we can do is that to convert them to the form that we're more familiar with. Okay, for example, cosecant, that's equals to 1 over sine. So we can replace cosecant x by 1 over sine x, subtracting cotangent x replaced by its equal, right? And then we actually get the same denominator. After we get the same denominator, we can use the common denominator, which is sine x, and we just minus cosine x and denominator sine x. So we have a 0 over 0 form. L'Hopital rule applies. Okay, so if L'Hopital rule applies here, we can take the limit of the numerator respectively. The derivative of the numerator is sine x. The derivative of denominator is cosine x. Right? And when x is approaching 0, of course, this is tangent x if you wish to write it that way, or you can just do direct substitution because this is a function. It's either way. You don't have to have this step, but it's going to be 0. So limit is 0. Okay. So number, yeah, that was the purple one, right? Let's see, let's do just a couple more. Example number 12. Example number 12. We have a limit situation. This limit situation is actually rather interesting. Okay, rather interesting. X is approaching 0. Wait, x is approaching 0. from larger than 0. So we have a limit. X is approaching 0 from larger than 0, and we're taking limit. And the function is in this form, 1 over x subtracting 1 over arctangent of x. What kind of situation is this? As x approaching 0 from larger than 0, 1 over x approaching positive infinity. How about this one? When x is approaching 0, tangent x is actually defined on all real numbers. Okay, let's think out aloud. Think out aloud. Okay, what kind of situation we have here? As x approaching 0 from larger than 0, right? 1 over x approaches positive infinity. But when x is approaching 0 for arctangent x, right? When x is approaching 0 from larger than 0, what does that approach? Tangent x, when x is approaching 0, arctangent x approaching 0 as well. If arctangent approaches 0, this will be approaching infinity. Okay? In fact, it approaches positive infinity. Positive infinity. So we have an infinity minus infinity situation one more time. So infinity minus infinity. And what will be the limit? What will be the limit? Well, we don't know. But one thing is certain, we have an infinity minus infinity case. Can we apply L'Hopital rule? No, we can't. But one of the things we can do, can we separately find the limit? We cannot either, because limit law will not apply, because the individual limits don't exist. All right. So the only thing we have left to do is to find the common denominator. So can we find the common denominator? One over x. So what is missing? We're missing tangent, arctangent over arctangent, right? Subtracting, this piece is missing x. So we're missing x over x. When x is approaching 0, right? But x is not a 0, right? By definition or limit, x is not possible. It is not 0, so we can do this. So once we find the common denominator, what we can do is we can keep the common denominator. Okay, the common denominator is x times arctangent. And over here, it's x times arctangent. So over here, that's an x, right? So when we combine these two, we have a subtract x. We have this form of the function. Arctangent x minus x over x times tangent arctangent x. Well, x is approaching 0. This is approaching 0. This is approaching 0. The numerator approaching 0. Denominator approaching 0. So we have finally a L'Hopital rule applicable case. We're going to take a derivative on the top and bottom. And what do we get? Right. So we're going to take a derivative of the top. The derivative of the top. Right, so let's just practice when we apply L'Hopital rule. The derivative of arctangent is 1 over x squared plus 1 minus 1. Right? The derivative of x is 1. What is the derivative of x times arctangent? Well, we take the limit using product rule. Okay, the derivative of x is 1 times arctangent, right? Adding the derivative of arctangent, which is going to be 1 over x squared plus 1. So the next step is going to be just like this. Okay, replace the top by this piece, and we replace the bottom by that piece. If we just organize the term a little bit, we kind of reduce it, right? We reduce this 1 times that when we omit the 1 and put the x on here. The denominator turn out to be like this. And then what do we do? Common denominator, natural, right? So naturally, we'll be thinking of multiplying the top and bottom by x squared plus 1. So that's the situation we're going to be doing. We're going to take x squared plus 1, multiply. So we use principle number 1. Okay. Now, when we are doing this, distributing the common factor, multiply that. That's going to be 1 minus -1 times this piece equals to parentheses that, right? And over here, x squared plus 1 multiply tangent, that's going to be that piece multiply arctangent x plus x, right? Because this piece times that, we have x left. If we organize the term on the top, right? Minus x squared minus 1, so we only have minus x squared. Okay. And then what? Then what? This is still doesn't look like we can get the limit, but still, let's see if x is approaching 0, that's approaching 0, and the whole thing is going to be approaching 0. So we have a 0 divided by 0 case again. So we can apply L'Hopital rule another time to see what happens. Okay, what I wish to tell you, I don't know the answer yet. Okay, I didn't know the answer yet. So, but we're going to continue, right? Negative x squared, the derivative of negative x squared is negative 2x. The denominator, right? This piece, we're going to use a product rule on this piece is just 1. So we're going to apply a product rule on here and plus 1. So don't forget the 1. So now we're going to focus on taking derivative of that piece. The derivative of that piece, so we take a derivative of x squared first. So that's going to be 2x multiply arctangent, right? Plus, we got x squared plus 1 multiply the derivative of arctangent is 1 over x squared plus 1. Okay, product rule applied in the denominator plus 1. Simplify. This piece makes 1. So we have a 2. Right? And now what do we get? Now what do we get? When x is approaching 0, the numerator is approaching 0, denominator approaching 2. Okay, denominator is approaching 2 because this piece on x is approaching 0, this piece is approaching 0. The good news is the denominator is not going to be 0. This is a continuous function on the entire number line. So now we can do a direct substitution, finally. Okay, so we're going to replace x by 0. And of course, this is replaced by 0. The final answer is 0 because the numerator is 0, denominator is not a 0. It takes so much work to do this, right? But do not despair. You can do it. You can do it. Okay. Last but not least, okay, it's number 56, or I will call it example number 13. Example number 13. Okay. We have a limit situation. Limit as x approaching 1 from larger than 1. And we have the function. The function are ln parentheses x raised to the power 7 minus 1 subtracting ln x raised to the power 5 minus 1. What can we do about this limit? This limit, what kind of form is it? Well, x is approaching 1 from larger than 1, right? So this piece is approaching 1 from larger than 1. So this piece approaching negative infinity. This is approaching negative infinity. So we have an infinity subtracting infinity situation again. But this time the situation is just so indeterminate form. Okay, indeterminate form of like that. So how can we resolve this issue? We can't apply limit law because either it doesn't have limit. This one approaching infinity, negative infinity, this one approaching negative infinity, right? So think out aloud. Right? This limit, okay, so what I'm going to show you. This limit, what I meant is that, okay, and this piece, they both approach negative infinity, and this approach is negative infinity as x approaching positive 1 from larger than 1, right? So we cannot apply limit law. We cannot apply L'Hopital rule either. So what can we do? Well, we can, first we can apply quotient rule inside the bracket. Okay, because this piece is positive, this piece is positive because the setting we're in. So we're going to take quotient rule, and of course, ln. Okay, and this is a 5, sorry, this is a 5. Okay, and what else can we do? What else can we do? Well, we know that if we can determine the limit, if this piece has a limit, right? I'm sorry, if this piece has a limit, then we can take the limit, go across the continuous function ln is, right? So for that reason, we're going to observe this limit. Okay, we're going to observe limit. So here I want to bring you to that. I'm going to observe this limit. As we are observing this limit, I'm going to show you the theorem that we are applying here. Okay, I'm going to show you the theorem we are applying. here. The theorem we are applying here, of course, has something to do with a continuous function. A continuous also has something to do with the this piece. This is the theorem I refer to. And what is the condition for this theorem? The condition for this theorem is, okay, be careful when we read these words. The limit of the inside function has to exist. So the limit on the inside has to exist. Okay. And then what do we get? If the limit on the inside exists, we can take the limit across the continuous function f is. Okay. So the inside function has to be continuous at the limit of the inside function. So that's why we observe this inside limit. So we're trying to see if this condition is satisfied. We are checking on this condition. Okay, we're checking because there's if f is continuous at b and this piece, right? So let me mark it for you. We're checking this condition. How come it doesn't? Oh, never mind. I have to reshare the limit. I reshare the screen. You probably don't see that. I'm sorry. Okay, here. So now you see the theorem, right? So what I'm trying to do here is that I'm going to mark. So this is the condition we're checking, which is the limit of the inside function, t. So our g is here, right? This is the g. So if you are to compare with our situation that with this theorem, the f, right? The f g of x, right? What is the f? The f is ln x. The f here is ln x. G, the g is this piece. Okay, so be careful that when we are applying these rules, we really need to know the contents of our stuff. Okay, so I'm going to, let me put it this way. Okay, so I'm going to put it this way. So that's why I'm taking this limit. You see, I drop the ln, I'm taking the limit, right, on the inside. And when we check the limit on the inside, you can see the numerator approaching 0, denominator approaching 0. So we can apply L'Hopital rule. So when I apply L'Hopital rule, okay, the derivative on the top is 7 times x raised to the power 6. The denominator is 5 times x raised to the power 5. And now what we get here is that ln, right? We can reduce this function. Wait, x to the power. Oh, this is a 4, sorry. Okay, this is a 4. Okay, so now when we reduce this function, we have 7 over 5 x squared. X squared. And then this function, this is a quadratic function, it certainly is continuous at 1. So the answer is just simply a direct substitution, which is 7 over 5. Replace x by 1. So the final answer of the inside the function is 7 over 5. Okay, you can see the procedure, right? We check the limit. Since we check the limit as such, now I'm certain that ln x, ln, which is the function outside, is continuous at 7 over 5. So now apply this theorem. Okay, this theorem about continuous function on composite function. We can bring the limit, okay, to the inside. We can bring the limit into the inside. So we're applying this theorem, okay? And of course, the limit inside is equal to 7/5, right? So this piece is equal to 7/5. So we can replace by the whole piece, which is ln, 7/5. That's it, it's done. If you like, you can say ln 7 minus ln 5, that would be the same thing. So you can see that every step of the way, we must make sure we follow the rule, we follow the theorem, right? So that's the kind of training we're trying to make sure you get. It has to be rigorous. It has to be rigorous. Okay. I think that's all for this lesson. I will make another one about using the logarithm. Okay, but I don't want to make this too long. So this is probably already over 1 hour. So I'll see you next time. Thank you for watching.